Let's look at some applications of geometric sequences. A shoe store is discounting shoes each month, and a pair of shoes cost $80. The table shows a discount for the prices of shoes for several months, and we are asked to find the cost of the shoes after 8 months. So the first month, the price of the shoes is $80, so this will be our first term. And we're using the formula A sub n equals A1 times R to the n minus 1. This is the explicit rule for a geometric sequence. And the reason we're using this and not the general form for an exponential function is that we're given the first month and not the 0 or y-intercept month. So we're going to substitute 80 for A1. So A sub n equals 80 times r to the n minus 1, and now we need to calculate r. So r is going to be, I'm going to take any term and divide it by the previous term. So 72 divided by 80, and I just chose to do that so that I wouldn't have to type decimals into my calculator, and 72 divided by 80 is 0.9. And we should have expected this value to be less than 1 because the y values are decreasing, so this is a decay function. So now we are asked to find the price after 8 months, and so we'll substitute 8 for n here and here. And so a sub 8, which represents the 8th term, is equal to 80 times 0.9 to the 8 minus 1 power. Then we'll evaluate that with our calculator, which gives us $38.26. This application problem can be set up one of two different ways. We can choose to focus on the start value, which is our 0 term, 0 to 100, in which case we'll use the general form of an exponential function, y equals a times b to the x. Or we can choose to focus on day 1, which gives us the input-output pair 1, 600, and then we'll use a sub n equals a1 times r to the n minus 1. So if you're given the first term, you're using this formula. If you're given the 0 term, you're using this one. So let's set them up both ways and see how they compare. So it says that we started with 200 cells. And then after day 1, there were 600, and after day 2, there were 1800. So again, if we're using an exponential function, we'll start with that 0 term. And we'll substitute this for our leading coefficient a. So that'll be y equals 200 times b to the x. Now where does b come from? B is our growth factor, our common ratio, and the number that we multiply by when we move from term to term in the pattern. And so I'll take any term, in this case, I'll take 600 and divide it by its previous term, 200, and that gives us 3. So our common ratio, or our base, our growth factor, is 3. Then this question is asking us to evaluate after 6 days. So we'll substitute 6 in the place of x. So y equals 200 times 3 to the 6th power. And we'll evaluate that, which is 145,800 cells. So now let's set it up using a geometric sequence and see how that compares. With a geometric sequence, we do not use a 0 term. We start with term number 1. So term number 1 will go here as our leading coefficient. So a sub n equals the first term times r, which is 3, to the n minus 1. This is our explicit rule for this geometric sequence. We'll do the same and substitute for 6n for n, and that will give us the sixth term. So a sub 6, which is the sixth term, equals 600 times 3 to the 6 minus 1. Then we'll evaluate 600 times 3 to the fifth, and that gives us 145,800 cells. So you see that an exponential function and a geometric sequence are basically the same pattern, and we just have two different ways of setting it up. The important thing to determine is, are we starting with term 0 at the y-intercept of the function, or with term number 1?